Okay, so mean value theorem for integrals also is pretty easy to remember, but not used as much, I suppose, or applied as much or seen as much on the AP test. So mean value theorem for integrals simply just says so because there's integrals, there's going to be area involved. So let's go ahead and draw a representative function f of x. Okay, and if we define the area, remember accumulation of area from a to b as the integral, what this is saying is that there is some value. I'm going to make it a different color here. I know I switched colors for A and B. I don't know why I did that, but there's going to be a value between A, B. So this for this part, that sounds like really familiar. That sounds like the mean value theorem for derivatives. Whereas derivatives, the main idea behind a derivative was slopes and tangent lines. This one's going to be about area. So what this says is that there's some value C, and this is just a picture, you guys. So it doesn't have to be exactly, it doesn't have to look exactly like mine. Okay, so there's some value C, so some x value between A and B, such that if you were to draw a rectangle with f of C as the height, so go ahead and put f of C as the y value. And let's say we were to draw a rectangle out of that. So I'm going to fully flesh out this rectangle. Okay, so the height of the rectangle is f of C. So the goal is, just like with mean value theorem for integrals, or sorry, for derivatives, you're trying to find a C value. This time, this C value, what it represents is that there is a rectangle out there that exists, according to mean value theorem of integrals, such that the area of the rectangle is exactly the area underneath the curve from A to B. Okay, so writing that out in an equation, what that's saying is, if I were to write the area of the rectangle, so let's start with area of rectangle. So it's saying that the area of the rectangle is equal to area under curve. So integrals, area, derivatives is slope, right? So area of a rectangle. In this case, if you guys look at the width of the rectangle right here, what's an expression for the width using the variables that you guys have there? I'm calling it the width, but it could be the base, whatever you guys want to call it. What's an expression for the length or the width of that rectangle? This. Okay, good. So that's basically our interval, which happens to be B and then minus A, right? So very good. Area of the rectangle is B minus A. And then times the height, in which case this is, the height is the Y value, F of C. Everyone follow where I got that expression right there, the area of the rectangle. And then if you guys can just have it on private chat and then chat along the way and let me know if you guys are following along. Does everyone get where the area of the rectangle comes from? Okay, perfect, thank you. Okay, so then now the area of the curve is from A to B. There's just the integral, right? The integral from A to B of f of x dx. Okay. And so if you guys look at this formula, so this is what's kind of neat with some of these things as you guys go along, is if I divide both sides by b minus a, I get f of c is equal to, actually before I rewrite it, does that look familiar to you guys, the right-hand side? Does that formula look familiar to you guys? What do you guys think it is? Yes, the average value of a function. Good. Yeah, so if I wrote 1 over b minus a over here, some of you guys wrote that is the average value of a function. So this is mean value theorem for integrals, is that there is some value c such that f of c is equal to the average value of a function. So steps are, just like there were steps with MVT for derivatives, you guys find the average value of a function, just like we did on yesterday's example. Step 2 would be you set f And we're just trying to find the x value c. This expression is just the function, right? So set it equal to the original function. And c happens to be your x value. So you solve for x and solve for x. Okay, so it seems easy enough. Just, apply the formula for average value of function. So obviously we would have to know that. I'm going to call this example 3, considering 1 and 2 were part of yesterday's notes. So let's say you guys were given a function. So what I'm going to do is have you guys do the first part of it just as a refresher for finding the average value of a function. And I think on the, if you guys did that metal wire problem, I saw someone ask, like, where did this, I forget what it was. There was a coefficient in front of the integral, and that person had asked, where did that coefficient come from? That coefficient came from, it was finding the average temperature. So don't forget, you guys have that 1 over b minus a part. Okay, so given that function, the question is going to say apply MBT for integrals. So a few of your homework problems will be like this tonight. So what I'd like you guys to do is do step 1 for me. So you guys are going to find f av. Okay, so I'm going to unshare the screen, or yeah, I'll unshare the screen and let you guys attempt this and see what you guys get. And feel free, if you guys find the answer, to type it out into the chat. It's pretty good practice for today's quiz. Remember, today's quiz, you guys have just general antiderivatives, which means that you have that plus c part and not have to deal with plugging in b and plugging in a, which is nice. Feel free to use calculators just for the computation of just, I would suggest plugging it in though, and then getting those values and setting up f of b minus f of a, just because, there's steps along the way. Of course, we can use the calculator to check our work, but it's useful, and to do fractions, things like that, but setting it up so that you have at least the b plugged in and the a plugged in is helpful for us to find out if we truly understand the first part of FTC. And again, feel free to use your calculator to do the fraction part. And then type it into the chat. Once you guys think you have the average value of a function, can you guys type it into the chat? Yes, it is that simple. So you guys, there's some coming through right now. The ones that have come through are correct. Keep typing. Again, the ones that have come through are correct. Yes, and let me go ahead and share my screen so you guys can see, and then we can move on to the next problem. So I just wanted to make sure you guys had a chance to check at least one of your average value of a function, but yes, the ones coming through are correct. All right, you guys, go ahead and check your work. You found the antiderivative, plugged in 5, evaluated it at 5, and then at 2, subtracted the 2, times it by 1/3 to get 1 as the answer. That was all step 1. That's just finding the average value of a function. Then step 2 is that you're going to take the average value of a function and set it equal to the original function. So in this case, we have 1 is equal to x minus 3 squared. Now at this point, you guys learned how to solve quadratic equations multiple ways. But one of the ways was if you have a quantity squared like that, oops, I put the plus minus in the wrong spot, that you can either FOIL everything out, isolate it on one side and then factor, or you guys could use the square root method at this point, particularly because you guys have a nice perfect square on the other side. So x minus 3 is equal to plus or minus 1. When we solve for the value, we add 3 to the other side, and we get 3 plus 1 is a solution, and 3 minus 1 is a solution. So both 2 and 4 are x values, but what we do is we have to go back and double check, well, do these x values even fall, these x or c values even fall within the given interval? And if you guys go back to the original, the given interval was 2 to 5. So we are good. X equals 2 and 4 fall between 2 and 5, inclusive of 2. So that's the solution. Those are the C values that they're looking for. Okay, are we good? Any questions so far? I think it's pretty basic. It's not too terribly difficult. Okay, we'll do one more. So 1014. I think that leaves us a good amount of time for, now this is example 4 for the proof. So same question, you guys, apply MBT. Again, good practice for the quiz, on the integration part at least. Okay, so I'm gonna leave just the screen on here and then work along with you guys, so you can feel free to look up. Just on your quiz, it's basic integration, so you're gonna look for ways to make your expression more simplified if there's a possibility that you guys can integrate term by term. So in this case, you have 4x squared. If I distribute, you have 4x squared plus 4 over a single monomial. So this can be also rewritten as, if you divide it into 2 separate terms, 4 plus 4x to the negative 2. Okay, so just rewriting the function so that it's just term by term, eventually that I can integrate by. Okay, so from there, again, we're gonna first step, MBT for integrals is finding the average value of the function. Again, that metal wire problem, for the person who asks, where did that number come from? That number comes from the 1 over b minus a. I think that was the part that you had forgotten. I forget what question part it was, maybe part C, average temperature. So 1 over 3 minus 1, the integral from 1 to 3 of 4 plus 4x to the negative 2. And I'll stay quiet here. Why don't you guys try to find your antiderivative and check to make sure it's correct. Yes, and feel free to move forward and solve the entire question, just verify that you guys got the correct F average. Yes, that's right, Tessa. Yes, someone just wrote 1 over b minus a will be my demise. I keep forgetting to do that to find the average value of function. And trust me, you're not the only person that, and I always emphasize that is like on a test, chapter test, warning is that some people, again, do those average value of function and they forget that 1 over b minus a. So kind of like if you want to put like a warning label or something, don't forget that. So yes, you guys are going to get to x squared equals 3. Just like make sure if it doesn't make sense, let me know. I just wrote number 2, setting the average value of function equal to the original, solving for it. I cross multiplied. I isolated the x squared term. I took the approach of the square root method, which then led me to plus or minus rad 3, which then some people might just box or circle in the multiple choice and say, oh, both of those are my solution. But wait, right? We have to go back. It must fall within this interval. And so even though plus or minus radical 3 was a solution here, only positive radical 3 is within that interval. So x equals radical 3 is your solution. In the chat, can you guys type into the chat if you're doing okay right now? Yes or no, because I have a good amount of time, actually. I think I can do this FGC. And I have a feeling this next response will be. So I want you guys to equate this. This is going to be the hardest proof we do this year. We don't really prove anything with series. It's just applications, application process. Again, this proof is just see how well you guys can follow along. You know, this might be a taste into like, okay, the college math class where you walk in and they're proving a theorem and you're just trying to follow along and see if it makes sense to you guys. This proof incorporates sandwich theorem in it. It incorporates limits in it. It incorporates derivatives and integrals, basically kind of like the main components of what we've studied so far are all meshed into this one proof. Okay, so as best as you guys can, I'll get your opinion afterwards, how you followed along here. Okay, so this is, again, most intense proof I would say we have all year long. So fundamental theorem of calculus. And this one is different. This one is part, and forgive me if I forget which part it is. I'm just going to call it part 2 because I covered it second. But your book and most books will call what you guys studied before part 1 and then this part 2 or vice versa. But the difference is the first one that you guys studied, just to recall, just to refresh your memory, let me actually go back to the first page so you guys can see it since I have time here. This was the fundamental theorem of calculus right here that you guys studied, is just be able to find the antiderivative and integrate to find the definite integral. Okay, and so that was just an application type thing. This one will at the end, I think when I explain it after I do the whole proof with you guys, it'll make a little bit more clear sense. Okay, so fundamental theorem of calculus part 2. Here we go. Okay, we have guess what? We start with another graph. of a function. Okay, this function I'm going to define instead of f of x, I'm going to call it f of t. Okay, so there goes the first part. Okay, so this is f of t instead of f of x. X I'm going to reserve for the x values that we see below as labels for it. So we're going to start with the leftmost x value we're going to call a. The next x value over we're going to call x. And then one more x value here. And so type along with me, you guys. If this is h units, if this is h unit in length, what would the x value, the far right x value be? If that's h unit in length, what is the, okay. And some of this I want you guys to just like participate by typing in, just so I know you guys are following along as we go and know where some of these labels come from. This is all just theory. Okay, so a, x, and x plus h. Now, if I define for you guys the area of x, let's say the area up to x, the accumulation of the area up to x, we would say that we could represent that using an integral. Okay, so the integral is going to go from, and you guys don't shade this part, but I'm going to show you guys. This is the area I'm referring to. What would the lower and upper limit of integration be for that integral? Just type the two letters in. What's the lower and upper limit of integration? Perfect. So you guys are still with me here. A and x. Okay, so a and x. The function itself is f of t, and we'll call it dt. If the independent variable here is t, you're going to see that this differential here is going to match that, f of t dt. That's all it is. Okay, so normally we've only seen f of x. You guys will tonight see like theta there. It's the same thing. It's like when you guys were taking derivatives, and the moment I switched to like, hey, take the derivative of sine of theta, a lot of you guys were like, wait, what? How does it change? It doesn't change anything. Okay, so then for the same process, this time I want you guys to set up an integral and tell me what the limits of integration are if we found the area of a of x plus h, which you guys see as the figure on the left. Can you guys tell me what your upper and lower limit of integration would be for that? Good. I think most of you guys say the left one is a, lower is a, x plus h is to the right. Okay, so what I'm going to do is now write out for you guys. And again, don't shade anything until this part right here. Okay, now shading wise, I'm going to erase the shading that I currently have. Can you guys shade in your, you don't have to type anything in, shade what you think this area represents, a of x plus h minus a of x. What area is that referring to? Or you guys can actually describe it into the chat first and confirm before you actually shade it. What do you guys think this is describing? The area of a of x plus h minus the area of a of x. What would that get you guys? Okay, the area, someone wrote the area between x and x plus h. Okay, so now what I'm going to do is take this integral right here. Okay, that's a of x plus h. I'm going to put it over here. And I'll put a subtract sign, and then I'm going to subtract that integral. So let's see if we can merge these two integrals. So simply taking the integral expression representative of the area and subtracting the two. Okay, there was a property of integrals in which if this, if I wanted to switch the upper and lower limit of integration, what I could do was take out a negative and then flip the limits of integration. That's allowed. That's a property of integrals, which I believe was covered in that video. So I'm going to do that right now and you'll see why. So the minus sign, this minus sign is still there. What I'm going to do is flip the lower and upper limit of integration and get x on the bottom here, a on the top here. Okay, minus a minus is plus. So I'll just do that instead of writing it out as a separate step. This is plus now, plus positive, like some people learned it in middle school. Do you guys remember, can I or can I not write this as a single? Yes or no, I can write this now as a single integral. Okay, yes, good. So, oops, that was not a highlighter. So yes, because this and this, the upper and lower limit of integration for both those integrals are the same. I have a plus sign in between. Let's merge the two. And can you guys look at the graph? Does that make sense with what you guys see on the graph? That the integral from x to x plus h represents the difference in the area. We're still good? Okay, just see yeses, so I'm assuming that we're still good. So I'm just gonna write this out here. So again, right now we have the area of x plus h minus the area of a of x, which is the area between x and x plus h, is represented by this integral. Okay, so let's go ahead and take this expression down, a of x plus h minus a of x. And we're gonna throw a little bit of Riemann sum into this, you guys. Okay, so all I did was write that. And go ahead and put that in between a compound inequality. Okay, remember that's the area between x and x plus h. And go ahead and shade that area right now if you guys would. This is the area that we're talking about. Okay, now I want you guys to think of, or tell me this. Does the left Riemann sum under or over approximates that area? Does the left Riemann sum under or over approximates? Okay, good. It under approximates. It's right here. Can you guys, this is the hard part. Okay, can you guys type into the chat, what is the area of that rectangle? What's the area of that rectangle? Okay, so good. I think some people are fixing their answers. For the most part, very nice, you guys. You have h is the width of the rectangle, and f of x is the height. So we're saying it under approximates, so we're going to say that it's going to go on the left-hand side of this inequality. Does the right Riemann sum under or over approximate your integral? Okay, so it over approximates. It's right here, determined by that point right there. So that rectangle is going to be an over approximation. So let's go ahead and write an expression for that one. So that one is h. It's still the same width. The height of it is, very good, f of x plus h. So you guys prepare to have your mind blown here. Let's see if you guys remember it from first chapter, okay? So let's divide everything through by h. Let's divide everything through by h. Every year I have a few students who recognize it, but does anyone recognize the middle? This a of x plus h minus a of x all over h. Isn't that cool? So some of you guys are seeing something familiar emerge. This part here, and this is what's so neat about this is this proof is that you start to blend in a bunch of things. So someone just said that limit thingy, the limit as h approaches 0. So let's stick that in there. So if I took the limit as h approaches 0 of each one of these components, all over h. Do you guys remember what that limit thingy represented? What did that limit? Okay, nice. Definition of the derivative. It is super cool. And I always debate every year, should I do this proof with you guys? Is it worth it? But I think it's just so awesome that you can bring in integrals, derivatives, limits, and it all comes together. So here we have the definition of the derivative. What's our function? Our function is a. So I can say that this is a prime of x. All of that is a prime of x. Now the sandwich theorem, okay? The sandwich theorem said that, remember, you had a lower limit and then an upper limit, and then you had your function in between. Well, then on this limit over here, there is no h to do a direct substitution in. So this is simply just f of x. It's not going to be affected. Over on the right-hand side, what happens when you guys plug in h into here? If you do h, if you plug 0 into h, you also get just f of x. And remember, that's what we wanted to happen when we were doing sandwich theorem, f of x. So all of this is saying is that a prime of x, its limit is also going to be, it has to be equal to f of x. It's sandwiched between f of x. So we reduced it all down to the derivative of the area is equal to f of x. Now we're going to take it one step further and go all the way back to the beginning. What was a of x? A of x was this expression right here. It was that expression right there. So I'm going to go back down and I'm going to say, well, if a prime of x is the derivative, I could simply say the derivative with respect to x of that integral above, I believe it was from a to x, of f of t dt must be equal to f of x. And that's it. This is the formula we were trying to get to. So again, I simply just replace a of x with the a of x that I defined at the beginning. And so if we think about it theoretically with the area, I know it's like what's happening is as you take the derivative, the h closes in. And so it becomes just, if you imagine the h closing into 0, it eventually just approximates it by the area being equal to the y value. That's really kind of theory based. But if you guys think of what this is saying, think of it on this level. When you take the square root of a number and then you square it, what happens, you guys? You take the square root first, then you square it. What do you guys end up with? This is called an inverse operation, right? If you take the square root of x and then you square it, you end up with just x. They undo each other. The square root and the squaring is simply just inverse operations of each other. So if you think about this, this is taking the derivative of an antiderivative or the derivative of an integral. So you just get back to the original function. And so there's lots and lots of applications with this. So I think it wouldn't be right if I just close it off there. So I want to do one example with this and then we'll just practice more. You guys don't have homework on this yet. Again, that was the proof. How did it go for you guys? Did it make sense? Okay. Awesome, you guys. Yeah, I think, yeah, and I do that every year. I always debate it, but you know, I think it's so awesome and it's cool to see all of those ideas come together. All right, so I'm going to show you guys the way to do this problem the hard way and the way to do it with FTC. Okay, so if you take a look, sorry, that says sine of t. Okay, so I'm going to equate it to this. This is telling me to do like the square root first and then square it, like inside out. So when I look at this, this is saying if I gave you guys this problem prior to FTC, you would do the integral first, like first, nested, and then the derivative second. That's what it would tell you to do. So we'll say, for this example, the old way. The old way is if I could have told you guys to do this problem prior to FTC and then after FTC. So let's say you guys were to integrate that. Okay, so let's practice for the quiz today. Can you guys find the antiderivative of sine of t? Okay, so what I'm going to do is, again, integrate first. Keep the variable the same. So if it's t here, it's going to be negative cosine of t. Notice that something funny is happening here where you guys have a definite integral, but one of the The top one is a variable, the bottom one is not. Okay, so that's fine. Let's go ahead and plug it in. Negative cosine of x. That's the upper limit of integration. And then we're going to minus or add cosine of -3. Okay, and that part was just simply the derivative, or sorry, the integral part. The next part is they're going to say take the derivative with respect to x. Okay, notice that when we integrated, the variables were t, so I kept it t. Then afterwards, when I plugged in the x, now we have an expression with x's in it, and now we're taking the derivative of that. Okay, if you guys take the derivative of negative cosine of x, we get sine of x, and that the reason is the derivative of cosine is negative. Negative times negative is positive. Sine of x. What do you guys think the derivative of this guy is? What's the derivative of cosine of -3? 0, right? It doesn't matter. And so later on, like I think you guys are going to do the new way so often, you're going to be like, why doesn't that constant matter? And then I'm going to say, remember when we did it the old way and we plugged in the lower limit of integration, then we ended up taking the derivative anyway, and it's just 0. So look at that. If you guys look back at the beginning, if you take the derivative of an integral, they just undo each other. So it makes sense that you get back to the original function, sine of x. Okay, that's the old way, the hard way of doing it. This is what you guys are going to do now. So if you see this type of problem, -3 to x, it's just rewriting the problem. I'm going to recognize first that it's asking me to take a derivative of an integral. The second thing is that the lower limit of integration must be at the bottom. The upper limit of integration is a variable. And what happens is you can just take that variable and plug it into here. And voila, your answer is just sine of x. You don't have to do that integrate, then derivative. It's just plug the upper limit of, and maybe I'll put it here, plug upper limit of integration in. Of course, there's all these twists we can take with this, right? What if the top limit of integration is x squared or x cubed or anything but x? What happens? What if the upper is a number and then the bottom is a variable? What happens then? So all these different things can take place, and that's what we're going to explore a little bit more next week.